Okay, so we're back and we're going to look at some examples now. All right, so this first one here, example 7.2, we are wanting to calculate the kinetic energy of a package. Okay, so we're supposing that there is a 30 kilogram package on a roller conveyor belt system, and it's moving at 0.5 meters per second. And again, we want to know the kinetic energy. Okay, so our kinetic energy is equal to 1/2 mv squared. Okay, so we can plug in our values. Our mass was given here as 30 kilograms. And our velocity was given as 0.5 meters per second. Okay. And so we plugged that into our calculator and we get 3.75 joules. Okay. So here is my kinetic energy of the package. Okay. Now, looking at our next example, 7.3, we're going to determine the work to accelerate a package. And we're going to be looking at the same package as we just did. We push the package with a constant force. Okay, so let's put a little picture here. So there's our package, and we push it with some constant force, which is 120 newtons. Okay, through a distance, so it goes some distance, whoops, of 0.8 meters. And we do have an opposing frictional force. So we have opposing force F, and that is equal to 5 newtons. Okay. Now we want to calculate the net, the net work done on the package. So for our first part, we're going to say our net work is going to be equal to our net force times our displacement times our cosine of the angle between the force and the displacement. Okay, and as you may have noticed, this example is similar to the one that I had here, what we were looking at. It's the exact same problem, okay? So I mentioned that there is going to be some kind of weight on the package, or of the package, but then there's a normal force, and so those two counteract each other, so we can ignore them for the problem. Okay, so our net force, and we talked about this already as well, is going to be my applied force, okay, minus my frictional force, since it's going in the opposite direction. Okay, so we have 120 newtons minus 5 newtons, which is 115 newtons. Okay, so now I know my net force. Okay, so my net work is going to be my net force, which is 115 newtons, times my displacement, which is 0.8 meters. Okay, and my cosine of theta, remember our theta here is actually 0 since they're going in the same direction. Okay, oops, sorry about that. They're going in the same direction, so our theta is 0, meaning our cosine of 0 degrees, this is just equal to 1. Okay, so our net work is just going to be the 115 newtons times my 0.8 meters, and so I get 92 joules. Okay, remember that 1 joule is equal to 1 Newton meter. Okay. All right, so that was the net work done on the package. Okay, So now what we're going to do is we're going to solve the same problem, but in a different way. Okay, so what we're going to do is going to find the work done by each of the forces that contributes to the net force. Okay, so our net force, remember, was our applied force here and our frictional force here. So we're going to find the work of each of those individually and then add those together. So my W of my applied force, so my work of the applied force, is going to be my force times my displacement, okay, times my cosine of theta, okay. And again, this is 0 degrees because it's pointed in the same direction. Okay, so we have 120 newtons times cosine, I'm sorry, times my displacement, which is 0.8 meters. Okay, put that into my calculator and I get 96 joules. Okay, now I'm going to do the same thing with my frictional force. Take my small frictional force, multiply it by my cosine of theta. So we get 5 newtons times my displacement, oops, times my cosine. And now this time my theta is not 0. Okay, so from my picture, hopefully, let me go ahead and erase a little bit. Let me redraw that. My displacement vector here, okay. My displacement and my frictional force, these vectors are in the complete opposite direction, okay? So what that means is if I were to plot them on a graph, okay, let me go ahead and pretend here. I've got my force, my frictional force in this direction, my displacement force in this direction, okay? What is the angle between them? My angle is going to be all the way here. So that is 180 degrees, okay? So my cosine, whoops, my God, whoa, hold on there. So it's gonna have cosine of 180 degrees, okay? And cosine of 180 is actually exactly -1, okay? So I'm gonna have a negative value here, and it's gonna come out to be 4 joules, okay? All right, so now I can calculate my net work by simply adding up all of the other works, okay? So my work due to my applied force plus my work due to the frictional force, that's gonna be 96.0 joules minus 4.0 joules, which comes up to be 92 joules, okay? So as you can see, this value is the exact same as the value that we just calculated. Okay, so both of these ways are acceptable. You may think that one is easier than the other, so you can do it either way. Okay? All right, so we're gonna go ahead and move on to our next example now. Example number 4, okay? And here, we're looking at the exact same problem, okay? Yeah, we wanna go to example 5. All right, so now we're wanting to find the speed of the package at the end of the push, okay? And we're gonna use energy and work concepts. Okay, so for this one, we can go ahead and remember that our net work is equal to, let me go back here, is equal to this, whoops, wrong way. This equation at the very bottom here, okay? So it equals 1/2 mv squared minus 1/2 mv naught squared, okay? And I can relabel these if I want to. This is actually the kinetic energy final minus kinetic energy initial, okay? This means the same thing, okay? But since we're looking at the speed at the end of the push, we are going to be looking at this speed here, okay? Or our final speed. You can put a little F down there if you'd prefer. I don't want to put too many scrub scripts, it'll get kind of confusing. Okay, so since we're looking for this value, I'm going to go ahead and switch around this equation here. And I'm going to say 1/2 mv squared equals our net work minus 1/2, oh actually plus, so I move that on that side, 1/2 mv naught squared. Okay. Now I'm going to go ahead and leave it in this form for a moment because it'll make it a little easier. So I'm going to put in my net work, which I actually found before, right? I found that in 7.3. I'm looking at the exact same problem, okay? Exact same setup, I should say. So my net work was 92 joules, okay? And this part here is my initial kinetic energy, which funnily enough, I found that in example 7.2, okay? So in this example, this was its kinetic energy as it was already moving, okay? And I got that at 3.75 joules, okay? So again, this initial velocity and therefore the kinetic energy initially is from the above problems, okay? So this gives me, let's see, 95.75 joules, okay? And again, that's equal to 1/2 mv squared, okay? Now I am just looking to solve for my speed, okay? So I can say velocity equals 2 times that 95.75 joules, okay, divided by my mass. Remember, my mass is 30 kilograms, okay? And this whole thing will be square rooted, and I get that my velocity equals 2.53 meters per second, okay? So this is my final speed as it was pushed, or at the end of the push, I should say. And it's final, okay? Now, there's one more part to this, which is example 7.5, okay? Now I wanna know, after that push, how far did the package go, okay? And I'm assuming that my friction is constant. Okay. So again, how far does the package go? So there's a couple of things that we need to know, okay? We have a package, right? And it was already moving with some velocity. And then it was pushed with some force, right? And it moves some distance, okay? And at the end of its push, it has some kind of velocity, right? Which we just solved for. Now, at the end of that push, okay, how how far does it, okay. At the end of that push, we're assuming that our velocity would go to 0, okay? At the end, okay, when it stops, okay? And so our kinetic energy at that point would also be 0, okay? So our kinetic energy final would be 0 at that point, okay? So we also want to find out what our kinetic energy would be to slow it down, right, to that stopping point. So our frictional force would have to be the exact opposite and equal to the kinetic energy at that position. Okay, so we're going to take our final, I'm sorry, friction, our frictional, and it should be this kinetic energy final, which is from, I think it's from example 7.3. I'm sorry, it's actually from 7.4, where we looked at this. So that's going to be right up here. So remember our final, when it's pushed, that's what we were looking at here. Our final kinetic energy after push, I should say, after push. Okay, so that's what we want. We want it to be the exact opposite of that. So I'm going to say negative 95.75 joules. Okay, because we want it to be negative of the kinetic energy from that one up there. Okay. All right. We also know how to calculate our our frictional, I should say friction, our frictional work. And that's going to be some kind of our frictional force, I'm sorry, our frictional force times some distance, I'm going to call it d prime, okay, times a cosine of theta, okay. Now our d prime is again going to be how far it went after that push. So what is this d prime? That's what we want to figure out, okay. This is this unknown that we want to know, okay. And again, as we notice, our frictional force and our distance that we travel here is going to be in the exact opposite direction. So it's going to be cosine of 180, which is just -1. So I'm going to simplify this and call it negative f times d prime. Okay. Okay. So if we go ahead and rearrange this to solve for my d prime, I get our W frictional, okay, divided by F, and there is also going to be a negative sign, okay? So now our distance is going to be negative times our frictional force, or I'm sorry, our frictional energy or work. It's going to be our negative 95.75 joules, okay, divided by our frictional force, which was given to us as 5 newtons. Okay, so then we get a value of 19.2. Okay, and let me go ahead and check our units real quick. Okay, remember that 1 joule is equal to 1 Newton meter. So if we have a joule divided by a Newton, we get our meter. Good, that's what we want. We want our distance in meters. Okay? So now this is the distance that it'll travel to a stop. All right. Okay, so I'm gonna go ahead and pause the video, and then we will, or stop the video and then come back with the next video looking at more types of energies.